All right, in this video, we're going to look at the first question on the worksheet. And part A says, sketch the vector fields f, which is equal to xi plus yj, and e, which is negative yi plus xj. So to start, let's say we're at this location, whose coordinates are xy, and I'm going to input this point into these two vector fields, and I want to sketch the corresponding output vectors. And for our reference, I'm going to go ahead and put in this position vector, whose tail is at the origin and whose tip is at this location, xy. And now this vector is just xi plus yj, which is the vector f, but from the convention we looked at in the last video, we said that for the output vector for a vector field, its tail is going to be at the location of your input point. So in other words, to draw the output vector for f, just translate this position vector so its tail is now at this point xy. So that is the output vector for f. And now for e, well, we're just swapping the components of f and putting a negative in front of y. So notice if I take the dot product of these two vectors, I get 0. So in other words, these two vectors are perpendicular. And if this point xy is in, say, the first quadrant where x and y are both positive, then negative yi says e will point to the left and xj will point up. So e would then look like this. Okay, so these two vectors are perpendicular. They have the same magnitude, right, which is just be the square root of x squared plus y squared, which is just the distance from the origin to this location xy. Okay, and so now what I'd like to do is plot a bunch of these, right? So as I let this input point vary, what do all my output vectors, what do they all look like? Well, for the field f, okay, any point you choose, the idea is just what we described here. You just take the position vector and then just translate it radially outwards, so its tail then is just at that input point location. Okay, so if you do that, you're going to get this field in yellow. Okay, so at any one of these points, okay, I've just taken the position vector for that point and then just moved it so the tail there is now at that input location. Okay, so you get this field of vectors that all point radially outward from the origin. Okay, so now to get this field in red, we're just going to take these yellow vectors and rotate them counterclockwise 90 degrees, and we'll get this field here. Okay, now something to highlight is that if I look at this family of concentric circles centered at the origin, since these yellow vectors point radially outward, okay, they're going to be orthogonal to this family of circles. Okay, so any one of these points of contact, right, I can see that the yellow vector and this circle are perpendicular. Now when I rotate 90 degrees, okay, these red vectors at these points of contact are now tangent to these circles. Okay, now we refer to the field f as a radial field, and more generally, any non-zero multiple of this field f is referred to as a radial field. And E, this is what's known as a rotation field. Okay, and you can think about this as, say, describing the force of a current, say, in some body of water. And if I threw, say, a stick in the water, then this field is going to rotate that stick about the origin. Okay. Okay, cool. So now, how about part B? It says, how are the fields G and H related to F and E? All right, well, I can see that G is just the field F divided by its magnitude. And likewise, H is just the field E divided by its magnitude. So let's go ahead and write that down. So G is just F divided by its magnitude. and H is the field E divided by its magnitude. So these two fields, G and H, they'll have the same direction as the fields F and E respectively, except since we're dividing by the magnitude, they're just going to have unit length. Okay, so here are the sketches of these fields. So you can see they point in the same direction as the fields F and E, except right, no matter where you are now, you're always going to have unit length. Okay, likewise here for green. Now, the only issue is at the origin. Okay, so notice for F and E, okay, these fields are defined everywhere. So their domain is all of R2. Okay, but at the origin, these two vectors, F and E, right, they're going to give you the zero vector. And so for G and H, you're going to have an issue when you divide by the magnitude. So here, the domain for each one of these fields would be all of R2 excluding the origin. So this backslash is saying we're going to take all of R2 except this single point, which is the origin in this case. Okay, so again, we're just simply dividing out by the magnitude to get these fields G and H, so we get these unit vectors. All right, cool. So these fields, the radial and rotation fields, are a really, really big deal in this subject, and we're going to see them come up quite a bit down the line. Okay, so that's going to do it here. See you next time.